barely came in last night, huh? Or yesterday. I was doing all right. Anybody know where this is coming from? Just Idaho in general. Okay. Yeah, that moose fire or whatever. I don't know. Most of the summer we've been okay. It's just the last couple of weeks it's been hitting us. And then when the weather changes, when it gets cool, it all goes away. And then when it gets warm again, then this comes back. So. All right, let's do this. Okay, we just finished normal tangent coordinate system. Okay, and then now the last coordinate system we're going to cover is polar coordinates, right? And this should be somewhat familiar to you. I think you've used these in multiple scenarios in the past. And then we will do relative velocity and relative acceleration, kind of discuss that for a little bit, and then we'll move on to kinetics. That's where we start summing forces, and that's equal to mass times acceleration. But right now, it's just straight up, still just kinematics, last coordinate system to cover. Okay, this one is similar to normal tangent, but different. Okay, and this throws people off sometimes. They get a little confused with this one, why you would use one over the other. I'll say this right up front. If you're doing a circle, if it's circular motion, it doesn't matter. Both of them give you the exact same answers, and you can use either one of those, okay? There's certain scenarios, there's certain scenarios in which one would be better than the other, like if a path is defined or something like that, but for the most part, I think we use this stuff for circles, so either one of these things will be just fine, okay? All right, so the way the polar coordinates works is we've got a vector that points from the baseline here to a point. So again, this is a path that this particle is traveling along, and we're going to define its position based off of the origin with a vector that's pointed at that. That vector we're going to call r, and it has an angle theta off the horizontal right there. Oops. That angle right there is theta. This is the x, this is the y. The origin's down here. And then the direction of this, or I guess what our coordinate system is, we have one direction that's pointed this way, and then another one that's perpendicular to that. This one right here we call ER, and this one is E theta. Right, and all ER is just a continuation of R. R goes along like this, and then ER points in the direction of R. So it just keeps going in that same direction. And then E theta is perpendicular to that. So that's that coordinate, right? If I'm down here, right? If I was down in a different location down here, then ER would be pointed out this way, and E theta would be this way. So you can see how that changes with, depending on the position, ER and E theta change, okay? So those are different. Those are different than normal tangent. Normal tangent coordinate, you would have one that was tangent to the path and pointed back to the instantaneous center of curvature. So that's what normal tangent would look like, okay? And so this is different. You know, certain cases they will align, right? If I imagine one here-ish, right? I'd have ER that way, E theta that way, and then that would actually line up with the tangent in there. So there are cases where they would actually line up, but the way I have it drawn right there, I put it out there specifically to show that they are different, okay? Let's define it, put that down in words, what these things are. ER hat is a radial unit vector. Okay, and E theta hat is perpendicular to ER in direction of increasing theta. Right, so in this case, theta, I kind of draw theta as going that direction. So theta is kind of getting bigger there, right? And so then it's in the direction of increasing theta, so it's that direction. If theta was going that way, E theta would be going this direction, right? So it just kind of depends on that, the direction of that. That's that's the definition of those coordinates, okay? When we define position, so we're going to do the same thing. We're going to define position, then we're going to take the derivative of that, and then get velocity, take the derivative of that, and get acceleration. So the position is simply this. What I have written down there is just r in the ER direction. So if I wanted to define the location of this position, or of this point, this particle right here, it's just the magnitude of r in the ER direction. It always is, right? Even if I'm down here, my ER direction is pointed that way, so the position is just going to be R in the other ER, right? Because the ER always is changing, so it's always in the ER direction, right? So that's the position. So we take the derivative of this, gives us velocity. The velocity vector is just dr dt. Take the derivative of the position with respect to time. This is dr in the ER direction. dt, apply the product rule, take the derivative of the first thing, dr dt in the ER direction, plus leave the first thing alone, which is r, and then take the derivative of the second thing. That's just taking that derivative and applying the product rule, so it kind of becomes these two things here. And we saw this before, and we used this before. When we take the derivative of a unit vector or a base vector, we had a identity for this. This just becomes omega in the E theta direction. Okay, and that came from an identity, so we'll just write identity over here. Right. Earlier a couple pages back, we introduced this identity. If you take the derivative of a unit vector, it just becomes omega times the other direction, right, perpendicular to it. And so that just becomes omega times E theta. And so this is what we get. The velocity I missed my highlight here. It's just r in the ER direction plus r omega in the E theta direction. So it's a little bit more complicated than the normal tangent, right? It was just velocity. It was just r dot, it was just r dot in the EN direction ET direction. This time there's two components to the velocity. Two components. We have the velocity in the ER direction, and then we also have this velocity associated with theta changing. So if we come back up to here, so we have, if I had a velocity in the r direction, it would include velocity that direction, and then r times omega causes a velocity in that direction as well, right? So you just take that radius times omega, and it gives you a velocity that way, and then just r dot in that direction. We'll do some examples. You can kind of see it play out, okay? So that's it. That's what velocity is. Two different components to the velocity. R dot in the ER plus r omega in the E theta. Acceleration now, we just take the derivative of this. And this thing kind of blows up on us a little bit because we have to apply the product rule a couple of times. So acceleration is equal to the derivative of the velocity with respect to time. The derivative, so we put this whole thing in it, r dot in the ER direction plus r omega in the E theta direction. All right. That dt. Okay, so take the derivative of that whole thing. And so we have to apply the product rule to this one and this one, right? So we're going to get 4 terms out of this. So let's go ahead and do that. This is r double dot in the ER direction. Take the derivative of the first thing, leave the second thing alone, plus leave the first thing alone, r dot d er hat dt, derivative of the second thing, plus Derivative of the first thing, r omega in the e theta direction. Oh, actually, actually this gets applied. This is three things. So we have to take the derivative of that thing, multiplied by both those two things left alone. Then take the derivative of this thing, leave those two things alone, and then take the derivative of this thing and leave those two things alone. So you have to do it because there's three items there. So that's the derivative of the first thing, left the other two alone. Then we get r omega dot e theta. So now I've taken the derivative of the second thing, left the first and third thing alone. And lastly, leave the first two things alone, dt. And then take the derivative of the last thing. Okay? So a lot going on there. This could be simplified some. One, you can simplify this guy, right? dE, this is taking the derivative of a unit vector, so this just becomes omega in the e theta direction. And this is derivative of unit vector. This is a little bit different. It's got a slight modification. There's a negative out front. Negative omega in the ER direction. Both of those are just back to that identity where you take the derivative of the unit vector. And you'll see that there's a couple of omega e thetas floating around, right? And so these things kind of combine. And what you end up with, once you kind of lump all the terms with the same unit vectors, you get this for acceleration. See how that sucker blew up on us a little bit. So the acceleration in polar coordinates is r double dot minus r omega squared in the ER direction. Both of those things are in the ER direction, plus r alpha plus 2 r dot omega in the e theta direction. Okay. The book kind of calls this first part, they can call it AR, and they call this part AR, and this part right here just A theta. Okay? So let's talk about what each of these terms are. They actually, each one of these, R double dot, R omega squared, R alpha, and R dot omega, all have a name, okay? And they all have a name and a meaning, okay? And they're all that's kind of the first part of using this, is trying to figure out what the heck each of these things mean. Okay. This is just a repeat of the equation up above. And let's kind of go through each of these things. R double dot. R double dot. This is a radial radial acceleration. I'm going to write this down and we'll explain it. Okay, so we're going to use this as an analogy. I forgot to initiate the analogy. So what we're going to use for this is a little exercise is a merry-go-round. You guys ever played on a merry-go-round before? See, they're dying, right? You don't run into merry-go-rounds very often anymore because all these kids would get hurt, okay? You know what I'm talking about? It's a big platform that spins around a circle. Who've all played on one of these before? Like the real deal. Look at you. Good job. If you look around at parks nowadays, you don't see them anymore. Okay? So there's a big circle and you're walking around. You've all stood on it and walked around, and then it gets you all wobbly because of all this stuff going on. Okay, this is a perfect analogy of when you would want to use it. When you would want to use polar coordinates, and it really demonstrates each of these components as well. So if I'm in the middle of this thing and I'm walking to the outside, right? Or I'm moving to the outside, I should say, right? I would have coordinates. This would be ER going this way, and then I'd have E theta going this way. Right, this would be if I had an omega going like this. If this thing's rotating this way, and then we're also going to draw as if there's an alpha going this way too. Right, so it's actually speeding up in that direction. It has an omega going that direction and an alpha going that direction. Oh, she's twitching on me here. Okay, so then what this R double dot is, it's the radial acceleration. So it'd be if I was right here, okay, and I was accelerating along the ER direction, right? So if I was on that merry-go-round and I started sprinting to the outside, that's the R double dot. So that the rate at which I'm sprinting towards the outside would be R double dot. Okay, that would be that acceleration. It'd be, I guess, not the rate at which I'm moving that direction, it's the rate at which I'm accelerating that direction. Okay, that's what the r double dot term is. That one's pretty straightforward. The r omega squared, what's that one? We've seen that, but we just covered that one last time. We saw it in normal tangent. R omega squared, centripetal acceleration. Centripetal acceleration, right? That is, you don't even have to be moving. If I am just at this location right here and the thing is whipping around, it wants to whip me off of there, right? If you're just sitting right there, I need to accelerate back towards the middle. If I do not accelerate back towards the middle, I go flying off of it. I need to apply a force. I need to accelerate back that direction. So if I was at that thing, it would be what I'd have to lean towards the middle for. I would have to accelerate back towards the middle by applying a force or through my feet and leaning that direction. I'd have to apply a force to accelerate back to the middle. Otherwise, I go flying off, right? So that's the centripetal acceleration. If I don't accelerate that direction, then I'm down. R alpha is the tangential acceleration. Tangential from omega increasing. Uh-oh. It's hard to type on that screen. All right. So if I had this omega, right? So it starts out at a certain angular velocity. If that angular velocity is increasing, then that would have acceleration. So if I was this person sitting right here, right? And somebody was increasing omega, right? They were pushing it, getting it going faster, making that omega going faster. I would need to accelerate in that direction, right? Because alpha was increasing, so then I have to accelerate that direction. That component with omega increasing, a velocity increasing, has to be acceleration. There'll be acceleration in that direction. That's in the e theta direction, right? All those are pretty straightforward. The last one, this one's a little less straightforward. This is 2r dot omega. Any guesses on what this one is? R dot omega. Anybody? It's associated with toilets flushing. Right? Toilets flush, and when they go down in a certain direction. It is the Coriolis. That's the Coriolis acceleration. Right? It actually has nothing to do with toilets. You've heard this before, though, right? Like in the northern hemisphere, toilets go one direction, and then the southern hemisphere, they go the other direction. Theoretically, the Coriolis is there affecting things, but really it's just plumbing is why that happens. They have their hoses come out one direction, we have ours come out the other direction. And anyways, but it's also, this is real. That's why storms in the northern hemisphere rotate one direction, and in the southern hemisphere they rotate the other direction. Right? That is at that scale. Coriolis absolutely makes a difference. But it shows up right here. This is Coriolis. This is Coriolis. No, Coriolis acceleration. I was going to put that. Okay, that one. All right, we'll spend a little more time on that later, but this one's a little bit different, right? These ones, I think, I can picture these ones pretty easy, right? Oh, if I'm sprinting towards the outside, obviously I'm accelerating. If it's rotating around, I need to accelerate back towards the middle. Otherwise, I go flying off at a tangent. If somebody's increasing omega, I'm going to feel a push behind me, right? If somebody's making this faster, I'll push behind me to make me speed up. I'll feel a push behind me to make me speed up. The Coriolis, though, that one's different. Okay, that one, but we got to spend a little bit more time thinking about that one. That would be So if I'm right in the middle, right, I would have zero velocity in the e theta direction, right? Because I'm stuck right in the middle. All I would be doing is going around circles. If I take a step out, though, if I go from here out one step, I would pick up a velocity that direction, right? I'm going from zero velocity, and then I would pick up a velocity of r omega, right? The further I go out, the faster I go. Before we defined the velocity, e theta, just to be r times omega. So if my r gets bigger, then I have to go faster. So if I was standing in the middle of that merry-go-round, I'm going around, and I take a step out, I have to accelerate to the new velocity of that new location, right? And so what that would feel like was like a push to the right, because I'd have to accelerate. I take a step out, it pushes me to the right. Then I quickly I start going that speed, and then everything's fine. Then I wouldn't feel that anymore. If I take another step out, I'd feel a push again. So everybody's done that. You've been on the merry-go-round, you try walking from one location to the other, and it's like pushing you to the side. What you're feeling is the Coriolis, right? At each level, right? Zero velocity and acceleration there, I gotta speed up. I take a step out, I gotta speed up. I take a speed out, I gotta speed up. Every level there, I'm going faster and faster as I move to the outside. So there's some increased acceleration as you go out, right? Which I think is an interesting one. We've all felt that before, but maybe they haven't called it that. But there it is. It shows up just like that, right? So just real quickly, like a difference between if you were dealing with a problem like this where I'm at the middle and I'm walking to the outside, that's a perfect example of when you would want to use polar coordinates. You would not want to use normal tangent coordinates because you remember I was talking about the path that it takes. If I start walking out, the actual path that I would take would be like this, right? Right? The path would look like that, right? I'd take a step out and then I'd be traveling around a circle. So normal tangent would not work for this one, right? Because you'd be like that, and my normal would be going this, or my tangent would be going that way, my normal would go that way. It's just constantly changing. But you could do this one in polar coordinates really well. So this is just kind of a really good compare and contrast between the different types of things. So let's spend a little second looking at merry-go-rounds real quick. Let's see if I got this. I've got one of these. Oh, they keep, hold on. I know it's not Friday, but so I get these. You see one? Where is that?
Soft, airy. Soft, airy.
Sorry. I can't get out.
You're looking at 6.
Okay. Where is it at? Right in the middle. Oh, right there. Okay, good. Okay. Preface this, trigger warning, or be careful, don't do this at home. Right? What happens is I always find I always put this in my library and then it keeps getting taken down, and so I have to go find it again. So these are people that are on merry-go-rounds and they get motorcycles or scooters or something like that to get these things going really fast, and then they sit on them and then they feel all of those accelerations that we were just discussing. Okay? Don't do this. See, he's feeling the centripetal acceleration, right? He needed to apply a force to accelerate towards the middle at r omega squared, and he did not, right? And he did not apply big enough a force, and so then he whipped back. This guy's helping. He did not last. That guy did not last.
Yes! I did it, Hoban! Let's go!
very nice of people to do that. They didn't move it away. I'm pretty sure nobody. Okay. You get the point on this, right? There's one. I was looking for one in particular. There's one where two guys duct tape their heads together. They have motorcycle helmets, and then they put their heads together, and they duct tape their heads together. I just wanted to see if I could see that one. These guys at least wearing helmets. That was his head. That was his head each time. Okay. So that could explain why they don't run into these very often anymore, right? It's because people are doing that, right? And then even just the classic ones, right? Like you could walk around, they had all those bars set up so that if you did fall, you would hit all the bars on your way off of it, right? And then, anyways. Okay, don't do that. Would you guys do that? You wouldn't do that, right? You would do that? Maybe? Survival of the fittest, right? I guess. Right? Take you out. Okay, special case is things moving in a circle. And when things are moving in a circle, this was pretty easy to talk about. R dot is equal to 0. And R double dot is equal to 0, right? There is no radial velocity and no radial acceleration. You're just fixed at those locations. So if you just go back up to this, right? If you go back up to this and R double dot 0 and R dot is 0, then those components go away. And then what you're left with is just this. You're just left with those two components, right? And that's just kind of close the loop here. If you're traveling in a circle, right? ER is just out like this. E theta is like this. Right? And so if you're not moving in the ER direction, right? You're at a fixed radius, then those two components go away. You're not going in or out, so R dot and R double dot are 0. And so you're left with this. So this is almost exactly the same equations for normal tangent for something traveling in a circle. The one difference is the sign on that R omega squared. The R omega squared term for normal tangent. Remember, normal tangent was pointed back to the instantaneous center of curvature. So normal tangent was pointed back that way, right? And so it was a positive R omega squared. But when we do polar coordinates, ER is pointed away, so your acceleration is in the negative ER direction. You're accelerating back towards the middle, so then there's just negative R omega squared, right? So if you're dealing with a problem in your homework or in an exam that is something traveling in a circle, something's traveling in a circle, you could use either one. You could do normal tangent or polar coordinates, either one. Okay. There's also a thing called cylindrical coordinates, okay? What you do is you just do polar coordinates in the XY plane. So you just turn this into a 3D problem, right? So you do polar coordinates in the XY plane, and then you just add a Z component. So that's all this is showing. All these equations is just showing the same thing. We'll use cylindrical coordinates on occasions. And so it introduces it in this chapter. So you just have R in the ER direction for position, but then you just add in a Z component as well. And then when you do the velocity, you have, this is just in the XY plane, R dot in the ER plus R omega in the E theta. And then you just take the derivative of Z in the K, right? And then finally for acceleration, you have all of this acceleration stuff, polar coordinates, and you just add on this acceleration in the K direction, right? So there'll be certain problems pretty soon that we're going to deal with. They're 3D problems, and the 3D problems you just do polar coordinates in one direction, and then just add in a Z component. So that you can imagine that those coordinates would look like a cylinder. So that's why they call it cylindrical coordinates. Again, just kind of close the loop here. before we do some examples. Right, you can convert between normal tangent and, you can convert between polar coordinates and Cartesian coordinates using this. So basically in your equations, when you're done, if you want to switch it over to Cartesian coordinates, everywhere there's an e theta, you put this. Everywhere there's an ER, you put this. And then it converts it over to the other coordinate system. Cool? Yeah. You betcha. These are posted online if you ever want to get the skeleton notes for this, yeah.
Do we have any reason to use spherical coordinates at some point?
We don't. I could imagine there being a situation that you would have to do that, but not in this class. We don't do that. How's that? I could add one in there if you want to. Yeah. But you're right. There is spherical coordinate systems in there as well. But the types of problems we do, this is just enough. Cylindrical coordinates are enough. You can also pair cylindrical coordinates with normal tangent if you want to do too. You just add in a z component. That's all you do. Pretty easy. Okay. All right. I'm going to do an example. I'm kind of just messing with these things here. This is our merry-go-round. Spinning with a constant omega. You start to walk to the outside with a constant r dot. Find A. Right? This is a pretty simple one. You're on a merry-go-round, start walking to the outside. So acceleration, just write down the acceleration equation. R double dot minus r omega squared in the ER direction plus r alpha plus 2r dot omega in the e theta direction. Okay. And so some key terms in here. It says the merry-go-round is spinning with a constant omega. So if it's a constant omega, then what's alpha? Yep. And omega is constant. That tells us that alpha is 0. Okay. And then you walk to the outside with a constant r dot. If r dot is constant, then what does it tell us about r double dot? It's 0, yep. This is just an easy one. And so basically up above here, r double dot 0, r double dot, 2 dots there. So basically up here, r double dot goes to 0 and r alpha goes to 0. Right, and so then what you're left with is that's the answer that we're going to use. It is just negative r omega squared in the ER direction plus 2r dot omega in the e theta direction. That's it. And one thing I forgot to mention with this Coriolis, in order for you to feel the Coriolis, you have to have a velocity towards the outside, right? And so, back to my analogy before, if I take a step out, I have to speed up. But if I just take one step, I have a little bit of velocity, and then I've now accelerated to the velocity of that particular level, and it goes away. I wouldn't feel that again. That side push goes away once you take that step. If I take another step, then I'll feel it again, but then it goes away. Take another step, and I'll feel it go away. So if you're not moving, you don't feel that Coriolis, right? And like I said, we'll talk about storms and why Coriolis makes storms spin one direction in the southern hemisphere versus the opposite in the northern hemisphere. We'll get into that, but it's associated with this. You have all this air moving towards the middle, and the Coriolis kind of curves it one direction. And down in the southern hemisphere, all this air moving towards the middle, it spins the other direction. Okay. That's why they say toilets do it as well. Okay, this one's a little more interesting. A block in a disc. So this little block right here can move inside of that disc. It's not in a fixed location, right? This one tells you polar coordinates, right? Because normal tangent wouldn't work because that path is kind of going in a spiral. So polar coordinates is your best bet here. That thing's moving around the slot. Moves radially outward in a slot with a speed of r dot is 4t meters per second. The platform rotates at a constant theta dot equal to 6 radians per second. block starts from rest at the center. Find the magnitude of velocity and acceleration at t equals 1 second. So there's a few things to do here. All right, so start out with velocity. The velocity is just r dot in the ER direction plus r omega in the E theta direction. And then just write down the acceleration. R double dot minus r omega squared in the ER direction plus r alpha plus 2 r dot omega in the E theta direction. Sometimes I like to just start by writing those things down, just so I kind of get a feel for what it is I need to know and where I need to fill in the blanks and stuff like that. So what they give us is r dot, right? They give me r dot, and that is 4t, 4 times time, meters per second. And then r double dot then would be taking the derivative of that, which would be just 4 meters per second squared. So I just took the derivative of r dot. Omega, they give it to us as being, that's also theta dot. They give that to us as 6 meters per, or radians per second rather. Right? And so then alpha is equal to 0. Just kind of fill in all the components that I have, right? Because I just took the derivative of the velocity, gives me the acceleration. Derivative of the angular velocity gives me the angular acceleration, so it's just constant. So then that just goes to 0. And so my velocity, we put in stuff we have here. That's just going to be 4 times t in the ER direction plus r times 6 in the E theta direction. Right. And so it's asking for the magnitude stuff. So right now I'm almost there. It's at t equals 1 second, so I can put in t equal 1 second. It'll tell me the ER direction. But what I don't have right now is what r is. Right? I don't know what the radius is. I don't know where, right? This block is moving to the outside. It's starting out the middle. It's moving to the outside. I don't know where it's at 1 second. So I have to figure out where it's at 1 second before I can finish the velocity. Okay? And so what we do is just come back to this. Right? This is just rectilinear stuff. So I'm going to say I need r. And so r dot is just dr dt, and now it's equal to 4t. I put the dt on the other side, right? So I just say dr is equal to 4t dt, right? So I just put the dt over on the right-hand side, integrate. This is going from 0 to r that I'm after, and this is going from 0 to 1. And by doing that, if I carry out that integral, I get r is equal to 2 meters at t equal 1 second. So there's what my r is. Now I just put that back into the equation. So my velocity vector is just equal to 4 times 1 in the ER direction plus 2 times 6 in the E theta direction. Let's just simplify that down. 4 in the ER direction plus 12 in the E theta direction. So that's the overall vector, but it asks for the magnitude. You get the magnitude by doing the square root of the sum of the squares. Often you just put lines on the outside. This ends up being 12.6. Okay. Any questions about that? All right, this is kind of why we started out with rectilinear stuff, right? Because we were able to use what we learned in the 1D stuff to apply to this curvilinear motion stuff in the polar coordinates. Just integrate that velocity equation to give me the position, which we did, and then we use that to plug it back into the equation above. Now this one right here, the next part, the acceleration, I think we have all the components. The second part is the acceleration. This is just r double dot minus r omega squared and er hat plus r alpha. Ooh. R alpha plus 2r dot omega in the e theta direction. Right? And then plug in all of our components here. I think we have them all. R double dot we found to be 4 minus r is 2, omega is 6, plus r is 2, alpha is 0, is 4t. We're doing it 1 second, so that's 4 times 1 times omega is 6. All that in the e theta direction. And so my acceleration ends up being equal to negative 68 in the ER direction plus 48 in the E theta direction. Meters per second squared. And then you do the magnitude of that, squared root of the sum of the squares. The magnitude of A is 83.2. Okay. Not too bad. Like I said, we're gonna do relative velocities here next, and then after that, I think the class gets easier. Once you start relating things to forces, it's very procedural. Draw a free body diagram, sum the forces equal to mass times acceleration in the different components, and then solve the problems. To me, it gets easier as we move along. This stuff is a little bit like, where do I start? Where do I go? What do I got going on? But trust me, it gets a little bit better. Okay, let's talk relative motion. It's our last kinematics topic. Let's get this started at least. All right, this ties back to when we were talking about base like reference frames. When we were talking about reference frames, we're saying, okay, if I was looking up, right, this back to this analogy that we used about if I was on an airplane and I was throwing, a frisbee between this guy and this guy, or if I was throwing a frisbee to one of my sons, right, and what is the velocity of that frisbee, right? Well, it depends on where you're looking at. If I'm looking at that from the ground, if I'm looking up, I'm down here on Earth and I'm looking up at this and I'm saying, how fast is that going? That thing's booking, right? Because it's going with 500 miles an hour plus the 10 miles an hour to 20 miles an hour that the frisbee's going. So it's both of those things added together. It's really whipping through there. But if I'm on the airplane and I'm throwing that thing, how it's coming at me is coming at me 10 meters per second, right? Or 10 feet per second or whatever it ends up being. Okay, so it is, or 10 miles an hour, whatever unit we're using there. So sometimes we want to be able to define the velocity of that thing relative to the Earth versus relative to something else, right? And this is where this relative motion comes in, right? I think Einstein was part of his theory of relativity and stuff. Is we really don't know what's not moving, right? How do you define what is not moving? It's very difficult to do that, and so it's also impossible to figure that out. Right? It's also what is the base there? Anyways, that's some deep stuff. So right here, let's define this. Let's come up with some equations to define this stuff. Okay, so if I'm talking about the position of A, right? I can go right to it, and then I'll call that RA. Right, the position of A. I can also define the position of A by going through B. I can go to B first, RB, and then I can go from B to A. Right, this is vector math. Right. So if I want to get to A, I can go over to B first and then go from B up to A. Right? Or I can go just from the origin right to A. Right? I could also go to A and then go down to B, and it would be the same as RB. Okay. So this is kind of the baseline of this topic. So RA This is position of A, both of these things, or B relative to origin. They call this the absolute position. Okay. Both of those things. If it's RA, it's the position of A. If it's RB, it's the position of B. So it's the absolute positions. The way I always state this as being the position of A as seen from B are relative to B. Whenever I see that little dat or that slash there, I always say in my mind as seen from, right? Just to make it really clear. It's I'm at B and I'm looking at A. It's important to grasp that. If I'm going to A from B, I go A as seen from B, or A relative to B. If you say that, it makes these problems a little bit easier. And so then the key here, or I guess the fundamental principle here, is that the position of A is equal to the position of B plus the position of A as seen from B, right? That's how I would say that, okay? And so we just did that in terms of positions, but if you take the derivative of those positions, you can get velocities. And so this is the key equation we use for velocity. If I want the velocity of A, it's the velocity of B plus the velocity of A as seen from B. Okay, and same thing, take the derivative again, it gives you the accelerations. So if I want the acceleration of A, it's acceleration of B plus the acceleration of A as seen from B. Okay, and then this further, if we go back to that plane example, if I wanted to figure out how fast that frisbee was going, you could say that the frisbee, the velocity of the frisbee, applying the stuff we had above, it would be the velocity of the plane plus the velocity of the frisbee as seen from the plane. Right? Just applying that equation up above to like a logical reasoning, right? If I want the total velocity of that frisbee, I'd do the velocity of the plane plus the velocity of the frisbee as seen from the plane, right? That's all these equations are doing. Oh, look at that. 13.164 is in your homework. It has a wrong answer in it. I'd write that down. The wrong answer in the back of the book and the wrong answer in the solutions manual if you're using that. So it's very frustrating to you guys when you're doing a problem if you're like, oh, I need to match their answer and then their answer is wrong. And so I think they have either they're both positive or one's positive or it's just off. So there's the right answer. So when you do that problem, keep that in mind. That'd be incredibly frustrating. Okay, we'll do the example next time. And so I think that we're getting pretty close. That's it. We have that one more example to do there, and then we're moving on to kinetics. So if you're printing out these skeleton notes, print out the next section for next time we meet. We'll probably get to the next section, which is kinetics. Now we're going to get into to me, the more exciting stuff, where we're relating forces to these acceleration equations and then solving these things from there. Go Beans. All right, happy Monday. Good luck.